Hello everyone. In this lecture, we're going to talk about multiple linear regression. So we're going to illustrate multiple linear regressions through the air pollution example. So this data is connected by General Motors. Response variable is age-adjusted mortality. Predictors. There are three categories of predictors. The first group is variables measuring demographic characteristics. And second group is variables measuring climatic characteristics. And the third group includes variables recording pollution potentials of 3 air pollutants. The research objective is to determine whether air pollution is significantly related to mortality. So those are the detailed description of the predictors. So the first one, January temperature, that is average temperature in January. So degree is Fahrenheit. And the mean July temperature. And relative humidity, annual rainfalls, education, median education, population density, percentage of non-whites, percentage of white-collar workers, population per household, median income, and HC pollution potential. And this NOx pollution is nitrous oxide pollution potential. And the SO2, that is sulfur dioxide pollution potential. Okay, now let's go back to the Excel. Let's have a look at the data. So this is the data connected by General Motors. So the first column is the city, different areas. Okay, so how many data we have? The first is a label. And so from the second row to 61 row, so we have in total 60 data points. Now this column is mortality as response variable. And we have January, July temperature, relative humidity, rain, education, population density, percentage of non-white, percentage of white-collar workers, population per household, income, median income, and HC pollution, NOx pollution, SO2 pollution. Okay. And here there are two yellow spots. As we can see here, we don't have any data. We have missing data over here. Now let's go back to the slide. So there are 60 data points. Pollution variables are highly skewed, and log transformation make them linearly symmetric. Okay. So the variables HC pollution, NOx pollution, and SO2 pollution are replaced by the log HC pollution, log NOx pollution, and log SO2 pollution. So in addition, observation 21, Fort Worth, Texas, has two missing values. So this data point will be discarded from the analysis. So in total, we are going to have 59 data points. So what we do is, so here, this is the HC pollution, NOx pollution, and SO2 pollution. Here I added 3 additional columns to do the log transformation. So this is another log 10 N2, because this is N2. If I double click, you see this cell is actually the log transformation of this cell. And the same for this one. And the same for this one. Okay, for SO2 pollution. So far, these 3 columns, we don't need them anymore because we have already did the log transformation. And then, okay, I think we cannot do that. Now, what we do is we cut this part and insert it over here so that we have it in the front. Let me see whether the numbers are correct. So it's still correct. Log Q2, log 15, and log SO2. So these are the X variables, and this column is my Y variables. And Dallas Fort Worth, Texas, this one has 2 missing values. So in this analysis, we delete this row, this data point. However, in regression analysis, we have different ways to do the missing data imputation. One way to do the missing data imputation is to calculate the mean of this column and put it over here. And or calculate the mean of this column and put it over here. But in this case, we have enough data points, so we just discard this this Fort Worth, Texas from the analysis. So now in total, we have 59 data points. Okay, now let's continue. So this one is a scatter plot of mortality against the selected predictors. Okay, so the y-axis is mortality. The x-axis is the general temperature, education, long white, and log NOx pollution variable. As we can see, there's certain kind of this one, the pattern is not so obvious, but there is some kind of pattern, but this one is very obvious. The mortality rate decreases when education increases, right? There's a decreasing trend. And this one, the long white, when the population long white increases, the mortality rate increases. And also there's an increasing trend over here. So there's a relationship between mortality and some predictors. So in order to investigate more, we have more investigation into the relationship. We're going to do the modeling. So what we're going to do is the multiple regression model. So we have Y is the response variable. We have our intercept, and we have predictor 1, predictor 2, and predictor K. So here is the January temperature, July temperature, and air pollutions. So what we did is similar to simple linear regression. What we want to do is to minimize the residue sum of squares. So this is our loss function. So this is residue because we have yi's observation. This is model prediction. And if yi minus this one, what is left is epsilon. And if we write it in the matrix form, this is a matrix form of the residue sum of squares. If we take this matrix, this equation involves the matrix, we take the partial derivatives with respect to beta, we will be able to get the least square estimates of the beta. So this is called LSE, least square estimation of the parameters. And that is X transpose X inverse X transpose Y. And we briefly discussed this part before in the regression and least squares. And in the next few slides, I'm going to show you a little bit more in details how to derive this beta. And not only this is a mean estimation of the beta, and this is a variance and covariance estimation of beta. So why this is called variance and covariance? Because we have one beta and we have k plus 1 betas. So the beta and beta has covariance. So in the diagonal, this is a matrix. So the diagonal is all the variance of all the betas. And the off diagonal is the covariance, for example, between beta 1 and beta 2. Okay? So we have beta 0 to beta k and beta 0 to beta k, the diagonal. The diagonal is the variance of each beta, and the off-diagonal items are the covariance matrix between different betas. Now let's have a look at how to derive the least square estimation of all the betas. The first step is to write this equation in the matrix form. So with the inclusion of 1, so for the constant, the regressor can be connected into a row vector. So this is a predictors. And thus the equation of each individual observation, because this is one observation and one set of predictor, this is corresponding to the one row here. We have yi, and we should have a column of 1, and this is the x1, x2, x3, and this is yi, xi1, xi2, xi3 to xi. How many we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right, 13, and 14. We have 14 variables. So this is x14, xi14. So this is for one observations, and this row multiplied by this column, we will get this equation. And if we write it in the vector form, it's 1 by k plus 1. This is a row vector. And this is a column vector, k plus 1 by 1. This is one column, plus epsilon I. So now we have 59 observations. So y1, y2 to y59. And this is our predictor, or we call it a regression matrix. This is a parameter matrix. Since each observation has one such equation, it is convenient to combine this equation into a single matrix equation. So if we check the dimensionality, this is n observations. We have n by 1 y's. So here is n by 1, 59 by 1 y's. And here is n by k plus 1. So k is 14. n by k, n by, so it's 59 by 14. So 59 by 14. So this block is 59 by 14. So you see here, 59 by 14 matrix. But we add a 1 because we need a column of 1. And this is because we have intercept. This matrix of the, this is actually a vector of the parameters is k plus 1 by 1 vector, column vector. And we have the residues or arrows, that is n by 1. So x is called a model matrix. Beta is the parameter matrix. Y is our response vector. So this is a parameter vector because it contains all the values of the explanatory variables for each observation in the data. Now, let's assume that because the assumption is epsilon follows the multivariate is a random multivariate normal distribution with expectation 0, and the variance is we only have this is an identity matrix. We only have variance in the diagonal term. So this is the assumption of my arrow term. So because we assume this arrow follows this distribution, it's a random. Arrow is random, uncorrelated. So 3 assumptions from simple linear regression. Mean 0, and we have constant variance in the diagonal term, and uncorrelated. So only the diagonal have the variance. We don't have covariance in the arrows. So since the epsilon are dependent on the conditional distribution of y, and y is also normally distributed with mean and variance as follows. So y, the mean, is actually x beta because expectation of epsilon is 0. And the variance of y is actually y minus mu transpose. This gives us this, actually this is the variance. Variance of y equals to the variance of the arrows. Because x beta is the deterministic part or systematic part, and then we add the random component epsilon, which makes the y becomes a random variable. And the y distribution is normally distributed with mean x beta, and this is a variance. Now, how do we get the estimation of the beta? So the idea is, this is our model, y equals to x beta plus epsilon. Now, what we need to do is to derive the matrix form of the residue sum of squares. So residue sum of squares, this is a residue square and sum of residue sum of squares. So this is residue transpose residue. So what we get is this equation, because y transpose times y and y transpose times xb So here y transpose times xb, and the b transpose x transpose times y, and b transpose x transpose times xb. So this gave us this equation. We can combine these two terms together. This is my residue sum of squares equation, and this is also my objective equation to be minimized. So we see that with respect to the beta coefficient, there is a constant y transpose y, because this is the data we have. That is the data y transpose y is over here. This column is my y. Now a linear form in beta and a quadratic form in, so this is linear form and this is the quadratic form in beta. To minimize the residue sum of squares, we find the partial derivative with respect to beta. So this is the partial derivatives, and we set it equals to 0. By setting this derivative equal to 0, what we get is x transpose beta equals to x transpose y. Then we multiply x transpose x inverse in both sides. Then we will be able to, so if x transpose x is non-singular, then we can invert this matrix. Then we can uniquely solve for the least square coefficient. This is a derivation, LSE derivation of the coefficient. So that is x transpose x inverse x transpose y. Okay. Now the analysis of variance, this is called ANOVA analysis. This is a total variation, same as before, correct total of sum of squares. So yi minus y bar and square, and sum them together can be decomposed into two parts. The part that can be explained by the regression model, then the part that cannot be explained by the regression model. So the part that cannot be explained is the residue sum of squares. So yi minus yi hat. And the part that can be explained by regression model is yi hat minus y bar. So this is my regression sum of squares. So same here, number of observations, n observations, minus number of parameters 1 and minus 1. And this is n, and we have k plus 1 parameters, so n minus k minus 1. And for this one, we have k parameters. Now, if we add these two degree of freedoms together, it should equal to the total degree of freedom. So if they don't equal to the total degree of freedom, then we have something wrong with the degree of freedoms. And this is the sum of squares, regression sum of squares, and this is a residue sum of squares, and a regression sum of squares, and this is a total sum of squares. The mean squares equals to the sum of squares divided by k, divided by degree of freedoms. And this mean sum of squares of the residues equals to this term divided by n minus k minus 1. So the explanatory power of the model, similarly, we use the proportion of the variation that can be explained by the model. So regression sum of square divided by the total variation. So measures the proportion of variation in y explained by the fitted model. And this R is called multiple correlation coefficient. Okay, this adjust R square. So RSS, we not only here we didn't take into consideration of the degree of freedom, but in the multiple linear regression, k sometimes is not 1 or 2 anymore. So we need to consider the k when we consider the residue sum of squares. So that's why we use 1 minus. So here the numerator divided by degree of freedom and correct, and the total sum of squares divided by degree of freedom. Then this will give us the adjusted R square. So in other words, adjust R square take into consideration of the degree of freedom in the numerator and in the denominator. So when an additional predictor is included in the regression model, R square is always increases, okay? Because regression sum of square will increase, but the total variation is just over there. When the model complexity get increased, the R square get increased. But this is not a desired property for model selection. So adjust R square, if we increase the number of parameters, this k will increase. So the adjust R square might decrease if the included variable is not an informative predictor. So usually adjust R square is a better measure of model fit. Okay. So similarly, we have multiple parameters. So here we have 14 variables, 14 predictors. We have k plus 1 parameters. And now we have 15 parameters. So we want to test which variable is significant. So if one variable is significant, then the beta should not equal to 0. So here we are trying to test the null hypothesis h0 beta j equals to 0 against the alternative hypothesis h1. So here it should be h1 beta j does not equal to 0. So here is a typo. And we are going to use the same test statistic beta j because this is t-test. We'll test beta j against 0 divided by the standard deviation. The higher the value of the t, the more significant is the coefficient. And also we have, this is a critical value approach, classical approach. And this is p-value approach. And we also have the confidence interval approach since we know the standard deviation. And this degree of freedom is the residue sum of squares, the mean sum squares of the residue. Okay, so this is n minus k plus 1 alpha over 2. We need to take into consideration of the degree of freedom. So t n minus k minus 1 alpha over 2 is the upper alpha over 2 point of the t distribution with n minus k minus 1 degree of freedom. If the confidence interval does not contain 0, then h0 is rejected. Okay. So here's the analysis of the air pollution data. So we have the constant and we have all the predictors. Okay, like that. So coefficient, those are the coefficient and those are standard deviation of the coefficient. And we use coefficient divided by standard deviation of the coefficient. We got the t statistics. And then we got the p-value. As one can see, if we compare to 5% significant level, we see this is a significant predictor, January temperature. And this one, rain, and population, non-white, is the significant variable. Okay, this is a very informative predictor for the mortality rate. And also this pollution, NOx pollution, is very important to the, actually strongly correlated to the mortality rate. And all the other variables are not seem to be significant. So the R square is 76.7, adjusted R square is 69.3, and this S is the square root of this term. Okay. So analysis of variance, ANOVA table, degree of freedom is 59 minus 158, and 59 minus 15. Why 15? Because 14 predictors plus 1 intercept column. 59 minus 15 equals to 44, and this is 14 predictors. So sum of squares, residue sum of squares, and the total variation. And if we add this term and this term together, it should equals to total sum of squares equals to the residue sum of squares plus the regression sum of squares. And the mean sum of squares equals to the sum of squares divided by the degree of freedom. And this 1196 actually equals to 52610 divided by 44. And we're going to compare the variation. These two variants, they are approximately in the same level. So we use this term divided by this term, we got the F statistics. And this is a p-value. It means that our regression model explains a lot of variation in the data. So the p-value is significant. Our variation model it can explain variation are not approximately in the same level as the random variation. It's more significant than that. So this is ANOVA table and the coefficient estimate. Now let's have a look at how to perform the regression analysis using the Excel. So again, we have go to the data tab and we have the data analysis tool pack. Now we select the regression. Yeah, we're going to select the Y range because we're going to include label, so we include the label. So this is Y range Now I'm going to include all the x range. Okay. Now we want to include the intercept, so constant is not 0, so we don't check this box. Otherwise, if we check this box, we will not include the beta 0 term. So we include the labels, and we want a confidence interval and the output. We want output maybe in the end. We output it over here, and we want a residue plot. Now we want to output it over here. Oh, this is input range. Input range was not selected correctly. This is the input. This is a y range. This is the x range. X range is correct. We have included the labels, and let's do the output. Okay, let's see the ANOVA information. Okay, now let's have a look at this ANOVA information. So this is R square, 76.7%. 76.7% is right. And adjust R square 69.3, standard error 34.5785. Okay, so it's correct. Now let's see the coefficient estimate. 133, so this is intercept, and all the coefficient estimate. We also have the standard errors. So standard errors, coefficient divided by standard error equals to t statistics, and also give us the p-value. This software automatically give us the p-value, and based on the p-value, we can see whether they are greater than 0.05 or not. As we can see, it's if we compare to the PPT slides, and all the results are very similar. It's almost the same. So significant variance are not in the same level. And this is the F statistics. So degree of freedoms, sum of square divided by degree of freedom is equal to mean sum of squares. The F equals to this term divided by this term. Now we have the 95% confidence interval for my beta. So this upper limit, lower limit, and upper 95% limit. And over here, we also see the residue plot for each variable. Okay, so in total, we have 14 variables. If we do the residue analysis, as we can see, the residue is approximately being 0, and do not have specific patterns. Okay, so this model is 76, can explain 76.7% of the variation in the data. Okay, so this concludes today's lecture on multiple linear regression, and we also showed how to do the multiple linear regression using the Excel software.